This is a video on acid-base chemistry. So why are we talking about acid-base chemistry? The reason is because metals are Lewis acids. So if you look at just a simple interaction with a metal and a ligand, you'll notice that the metal has empty orbitals to accept ligand electrons. And so a metal-ligand interaction is simply just a Lewis acid-base reaction where the metal is the Lewis acid and the ligand is a Lewis base. To demonstrate what happens when you add metal to water, I'd like you to pause the video and try this problem as a review from general chemistry. So this problem is asking you to write the balanced equation for water or for the dissociation of water, and to determine what the hydrogen ion concentration and pH are in pure water. Here I've given you the dissociation of water equation. You could also have drawn it with two waters going to H3O plus and OH minus. The equilibrium expression is written here, and since the problem tells you that the pK of water is 14, you know that the Ka for water is 10 to the negative 14. And so if you know that the hydrogen ion concentration and the hydroxide ion concentration must be the same, then you can solve for this hydrogen ion concentration, which is 10 to the negative 7th, or pH of 7. Now, when water is bound to zinc, the pKa of water is 10, so it's lower, which means that the equilibrium actually goes more to the right. Here's the analogous chemical equation where you have zinc bound to water, and it dissociates into hydrogen ion and zinc-bound hydroxide ion. If the pKa is 10, then the Ka is 10 to the negative 10. Here's the equilibrium expression. And to solve this, I need to remember what I did in general chemistry, where I know the initial, the change, and the final concentrations. In this case, initial is 0.1, change is x or negative x, and so the final concentration of zinc water is 0.1 molar minus x, and then the concentration of the two products are x. And now I can plug into the equation and solve. I should get hydrogen ion concentration is 10 to the negative 5th, which means my pH is 5. So by adding zinc to water, I can drop the pH, or basically I'm increasing the amount of hydrogen ion concentration in water. So by this definition, zinc, or metal itself, is a Lewis acid, but it's also a Bronsted acid because it's producing hydrogen ion in water. Now, why does this happen? This happens because the water-metal bond polarizes the water. So if I look at this bond, this is polarizing the water, and it's displacing some of the electron density from the oxygen to zinc. And so it's weakening these oxygen-hydrogen bonds here, and therefore pushing the equilibrium forward where hydrogen ion is dissociating. On the other hand, I can think of this as zinc stabilizing the conjugate base here. So if this was hydroxide ion by itself, it would be much less stable than the hydroxide ion bound to zinc. And so in either case, however you look at it, you are promoting this reaction to go forward, and so you're increasing the Ka of water, and you're decreasing the pKa, and in turn decreasing the pH of the water, or the water solution. Now this happens because there's a coordinate covalent bond here. Coordinate covalent bond has covalent character. It's essentially covalent. We treat it a little bit differently because we don't put any kind of formal charge on oxygen based on this bond. So it's covalent in nature, but we treat it a little differently when we draw the structures. In contrast, alkali metals don't have coordinate covalent bonds. So something like sodium does not have a coordinate covalent bond. Its interaction with a Lewis base like water is purely electrostatic. So this is an ion-dipole interaction, not a covalent bond, whereas up here, when you're dealing with a D-block metal ion, you have more covalent character, which allows it to affect the acidity, or the pKa of the water. Now the main difference here is that the zinc ion does not have a closed shell, and so it has orbitals on zinc that can accept electron density from the water. And so you can think of this as the highest occupied molecular orbital on water is going to donate electron density into the lowest unoccupied orbital on zinc and form a new covalent bond or a new molecular orbital. On the other hand, the sodium has a closed shell. It doesn't have any orbitals that can accept electron density from water. And so again, this is purely electrostatic. It's an intermolecular force, not a bond. And so alkali metals in general don't have available orbitals with which to accept electrons from bases. And so again, purely electrostatic. If we look at this, again, we're going to focus on an acid-base reaction, and we use molecular orbital theory to explain this. For this case, I'm going to use a familiar example of NH3 interacting with hydrogen ion, but you can extend this onto metal systems. So let's use an example that you've seen recently. The molecular orbital diagram for ammonia, NH3, is formed from the atomic orbitals of nitrogen and 3 hydrogen salps of compatible symmetry. When you make this molecular orbital diagram, it looks like this. And here my HOMO, or my highest occupied molecular orbital, is an A1. It has A1 symmetry, and it's the highest occupied orbital. It's got those electron pairs right there. So now to see how NH3 would interact with an acid H+, I'm going to get rid of my atomic orbitals and just look at the molecular orbitals for NH3. Again, here's my HOMO. It has A1 symmetry. This is in the C3V point group. The symmetry labels I have here are the C3V point group. Now it's going to interact with a hydrogen ion. The hydrogen ion has an s orbital, and it has compatible symmetry. I'm just going to label this as A1, but an s orbital is able to interact with the A1 orbital of the NH3. Now when they do interact, the resulting molecule is going to have a different symmetry. It's going to have tetrahedral symmetry. And so I'm going to change the symmetry labels that I'm using on these new molecular orbitals. But what's going to happen here is that the A1 is having compatible symmetry with the A1 HOMO here. It turns out that it's also going to have compatible symmetry with these two E once it's transformed into the tetrahedral. So to simplify here, I'm first just going to write my molecular orbitals, the A1s that are not going to interact strongly. I'm just going to write them right in there. And again, this is a simplification just so that you can focus on the important part. Now what's left over is these A1 and the E1 group. And what's going to happen is the A1 and the E1 group are going to interact with this A1 LUMO on hydrogen to give you a new T2 set. Okay, the symmetry labels have changed because I've changed my symmetry. So the A1 and the E1 combine to give you T2 bonding and T2 anti-bonding orbitals on this new molecular orbital. Or sorry, this new molecule or molecular orbital set. And the same thing can happen with D metal ions. So D metals have orbitals. Normally they're the d orbitals, but they don't have to be. But they have available orbitals that electrons from the Lewis base, or in this case I'm showing water, the electrons from the oxygen here can donate into the metal ion. The metal orbitals can accept electron density from the ligand and in either a sigma bond or a pi bond fashion, and they really polarize this bond, which weakens the hydrogen electrons. So because D metals can accept electron density into their orbitals, they have the effect of demonstrating acidity in aqueous solution. There are different types of metal acids that we're going to see. And the ones that I've just shown you, basically where a metal is interacting with water and it's making the water more acidic, these are aqua acids. So here I've shown the first dissociation of an aqua acid with two waters. This is still an aqua acid because the next dissociation is going to be from this water. So anytime a hydrogen ion is dissociating from a water bound to metal, the acid species is called an aqua acid. Once you've deprotonated all your waters so that you only have hydroxides left bound to the metal, now you're talking about a hydroxo or a hydroxy acid. It's spelled differently depending on which source you're getting your information from. But the important thing is that the hydrogen is coming from a hydroxide bound to a metal ion, and the metal ion does not have any oxo groups. So over here, you see once you've deprotonated one of those hydroxide groups, now this double bonded oxygen is an oxo group. The next association is also going to come from hydroxide, but this is defined as an oxo acid because of the double bond oxygen. So the difference between a hydroxy and an oxo acid is just the presence of this double bonded oxygen. Once you've got all oxides, or the hydroxide, or excuse me, once you have all of the oxides, now you're talking about an oxide. It's not a hydroxy acid or an oxo acid anymore. It's not even an acid, it's just an oxide. So actually these kind of species, these oxides, can demonstrate basic properties going in the reverse direction here. Now let's talk about trends in the D metal cations, the aqua acids. In general, the alkali metals, group 1 demonstrates absolutely no acidity. Group 2, very, very, very weak acidity. They're not really considered acids. The D block metals are where you see most of your acid behavior, and the strength of the acid depends on the charge and the size of the metal. So in general, +2 metals are weak acids, +3 metals are moderate, and +4 are strong. And in general, the size of the metal ion will also affect the acid strength. The smaller radius and higher charge you have, the stronger the acid. So a +2, like iron +2, will be a stronger acid than ruthenium +2. And likewise, manganese +4 would be a stronger acid than rhenium +4. In general, the oxides are basic, so once you've deprotonated the aqua species completely, you've got oxides, and those end up being bases. So examples are manganese +7 exists as manganese or MnO4+, and chromium 6 exists as CrO4 2+. These things are bases because they actually interact with water to remove a proton from water and create OH- in solution. And in general, it's useful to know that the solubility of the metal hydroxide species that are resultant from the deprotonation of aqua species, they can tell you, well, basically they correlate with the trends in acidity. So iron +3 is a stronger acid than iron +2, as you would predict from these rules up here. And when you deprotonate the aqua species to make the neutral metal hydroxides, these things are not very soluble in water, but you can see that the iron 3 hydroxide is much less soluble than the iron 2 hydroxide, and that's because iron 3 is much more acidic than iron 2. Speaking of oxides, these things can actually demonstrate both acid and base behavior. The metals in general are going to form basic oxides. That means that their oxides react with water to actually abstract a proton from water and give OH- in solution. Acidic oxides are generally those of the nonmetals. The most common one that you're probably familiar with is carbon dioxide. When you dissolve carbon dioxide in water, you get carbonic acid and you produce H+ in water. So that's what it means to be an acidic oxide. Those are the things that you find over here on the side with the nonmetals. In between the metals and the nonmetals, you have metalloids, and those things usually produce both. They can demonstrate both acid or basic properties, and so they're called amphoteric, or they demonstrate amphoterism. And then the acid-base properties of the oxides of D metal ions really depend on oxidation state. As far as oxo acids go, oxo acids are not typically transition metals. These are things that you will usually find the alkali metals or the nonmetals forming oxo acids. Most common ones that you probably know of are nitric acid, sulfuric acid. And there are no periodic trends, but there are trends that are based on the number of oxides and the number of hydroxides that are bound to the element. And these can be predicted using, the strength of the oxo acid can be predicted using a set of rules that don't depend on the element at all. They only depend on the number of hydroxides and oxo bound to the element. So these are Pauling's rules, and they're Pauling's rules for predicting oxoacid strength. So for any oxoacid of the general formula, so P is the number of oxo groups, and Q is the number of hydroxides, and E is the element. When Q is 1, so that means when there's only one proton or one hydroxy group that will release a proton, the pKa will usually be, or it's predicted to be, 8 minus 5p. So 8 minus 5 times the number of oxo groups. And the number of oxo groups will decrease the pKa or increase the acidity because oxygen is an electron withdrawing group, and so it increases the acidity of this hydrogen. Now, when Q is more than 1, so that when there's multiple hydroxide groups, then you have multiple pKa's because you have multiple hydrogens that can be released. And here you have pKa1 is just the same as it would be. pKa2 increases by 5, and pKa3 increases by 5. So you increase by 3 units. And sorry for this mistake, this should be pKa3. You increase by 5 units for every subsequent proton dissociation. Trends in binary acid-base strength. So now we're talking about just hydrogen bound to one other type of element. These usually can be simply predicted with electronegativity, and they correlate directly with electronegativity going across the periodic table, and are actually opposite to electronegativity going down the periodic table. So if you compare, for example, CH4 to NH3 to OH2, your acidity increases going across because of electronegativity of the atom. And going down, HI is actually most strong in the series of haloacids. So HF is the weakest and HI is the strongest, and that's because the size of the atom really matters. So I being the largest atom and F being the smallest atom, F makes a very strong bond to hydrogen, and I does not because it's very large, and so the energy difference of the molecular or the atomic orbitals from H and I, it's very different, so they don't form a very strong bond, and so it results in HI being very acidic. Inductive effects are also important, so you should know these from your coursework in organic chemistry. And so if you compare pH3 to pHF2, you have 2 electron withdrawing substituents on here that would make this hydrogen more acidic, and it would also make this electron pair more or less basic than this electron pair and compared to that hydrogen. So in general, you can rely on those trends. A major exception is BX3 or ALX3. These are common catalysts that you've probably seen in organic chemistry. They're Lewis acids because the boron, the aluminum are 6 electron species, and they are electron deficient, so they will accept electron pairs and act as Lewis acids. So based on the inductive effects of these electronegative elements, you might expect that BF3 would be the most acidic and BBr3 would be the least acidic. But in contrast to what you'd expect, the weakest acid is actually BF3 and the strongest acid is BBr3. The reason for this has to do with the fact that the p orbital on the boron can overlap with the electron pairs on the halogen. So here's a general structure where I have my p orbital in blue, and I'm showing that the electron pairs on the halogen should be able to interact with that p orbital. Now, if the size of the orbitals on the halogen are comparable to the size of the orbitals on boron, you have good overlap, but in this case, fluorine is the example of a good overlap. Chlorine is too large and bromine is even larger, and so there's not good overlap between the boron orbitals and the chlorine or the boron orbitals and the bromine. And so here you have almost a pi bond between the halogens, the fluorine and the boron here, whereas you can't have that sort of stabilizing effect with chlorine and bromine. So p orbital overlap in this case can lead to pi bonding, which stabilizes the acid and makes it less reactive. Other trends, you can expect that electron donating substituents increase basicity. If we look at the gas phase basicity of amines, so this is trimethylamine, dimethylamine, methylamine, and just ammonia, you would expect these methyl groups to donate electron density and increase the basicity of the electron pair here compared to here, and that's what you see. So when you're reacting these different amines with hydrogen ion in the gas phase, this is the most basic and the least basic. Things that can interfere with this trend are sterics. So you take a bulkier acid and react it with this series of bases, you see that now this base is not quite as basic as you would have expected based on the inductive effects, and that's because of sterics. So these guys are blocking your BF3 from coming in. So now you have the trend of most acidic, next most acidic, then this one, and then the ammonia is last. Solvation can also interfere with these trends, and notice that if you have water as a solvent now instead of the gas phase, you've also changed the trend that you would expect based on inductive effects alone. Again, here you've got this trimethylamine being much less basic than you would have expected, and the reason for this is because of solvation. If you look at the conjugate acids of those bases, down here the ammonia, or the ammonium ion, can be solvated very well because it has 4 different hydrogens that can hydrogen bond with water. Here we have 3 hydrogens that can hydrogen bond with water, and the more hydrogens you replace with a methyl group, the less ability for that conjugate acid to be solvated. So in this case, it decreases the acidity of this trimethylamine because its conjugate acid cannot be solvated well by water. So the solvent can affect the trend in acidity or basicity. In fact, that's a good time to mention that solvent really does matter. So water as a solvent, this is an amphoteric solvent, which means it can act as both an acid or a base. And anytime you add something into water, the strongest base that can exist, or no matter if you add a stronger base than water, you're just going to get hydroxide ions in solution. If you add an acid that's stronger than water, you're only going to get the H3O ion. So the strongest base that can exist in water is hydroxide. The strongest acid is H3O plus. And so that's why in water, we can't distinguish between these 4 different strong acids. So in water, a solution of nitric, sulfuric, hydrochloric, or hypochloric acid are all going to have similar acidities. On the other hand, if you use acetic acid as a solvent, now your strongest acid is the conjugate acid of acetic acid, and the strongest base is the conjugate base. And in this case, you can actually distinguish the different strengths of these 4 acids. So nitric is the weakest, sulfuric is next, hydrochloric, and then hypochloric. In your textbook, you'll find this figure, and this is relating to this the solvent matters idea. Now, the leveling effect is it's basically where acids or bases are brought down to the limiting conjugate acid or base of the solvent. Okay, so in this case, that explains why these 4 acids have equal acidity in water, because they're limited by these 2 things. And over here, we are not limited quite as much. Your pH range with water is 0 to 14, and your pH range in acetic acid is from -10 to +10. Now, this is a chart that shows you the pH ranges for different solvents, and so if you want to distinguish something, that has a pKa somewhere of like -5 and something else that has a pKa of 0, you can't do that in water, but perhaps you could do that in hydrofluoric acid or methanol. Dimethyl sulfoxide, DMSO, is a really good solvent for determining pKa's of acids in a broad range. You can see that this has one of the broadest ranges of the solvents shown here. But again, the leveling effect is where acids or bases are brought down to the limiting conjugate acid or base of the solvent. And this can really affect how your acids and bases are behaving. All right, there's one more thing that you should know about acids and base behavior, and this is hard-soft acid-base theory. This theory classifies acids and bases by their polarizability or by their charge to size ratio. So things that have high charge and small radius have high charge to size ratio, and they are not very polarizable. They have very dense charge, and these things are defined as hard. I think of these as little baseballs, like they're very hard and compact, compared to things that are soft, which are very large and they have lower charge, so they have a lower charge to size ratio. And these things are kind of like, in my mind, squishy cake balls that are very polarizable. And this theory says that hard acids like to bind to hard bases, and soft acids like to bind to soft bases. We also have an intermediate character called borderline, and it's just basically things that are between hard and soft. So if you look at the periodic table and you look at table 4.5 in your textbook, you'll notice that the things that are defined as hard acids are the things that are up towards the top left-hand corner of the periodic table. Things that are soft acids are the things that are kind of down here toward the lower corner of the D blocks. And in general, in the transition metals, the hard or soft character depends on the charge and the size of the atom. So you'll see something like copper 2 is a borderline metal, but its lower charge partner, copper 1, would be soft. So here you see copper 2 is borderline, copper 1 is soft. Iron is not written here, but iron plus 2 is borderline, and I would classify iron plus 3 as a hard acid. Bases, similarly, the smaller negatively charged bases are going to be up at the top left-hand corner, are going to be up at the top right-hand corner of the periodic table. Your hard bases are oxygens and nitrogens and fluorines, and borderline things are nitrogens that are part of conjugated systems that are more polarizable, and larger atoms like bromine, and then your soft acids, things like thiols. This is a really useful theory to know because it really does predict a lot of acid-base behavior, especially with metal ions and their ligands. All right, that's the end of the video. Please make sure you do your reading, and I'll see you in class.